Previously, we looked at a video in which we defined what a Riemann sum was with regards to this area problem and gave some notation. In this video, we're going to look at another example of a specific function and an interval, and we'll be using a Riemann sum to approximate a certain area. So let me go ahead. So this is just another example. And let's use a trigonometric function. In fact, it's the composition of the sine function and let's say our x squared function. So sine of x squared is our function, and let's take the interval to be from 0 to 5. And let's use n equals 3 subintervals. Right, and let's use a right Riemann sum or approximation, right? So let's work through. Oh, that doesn't look like two ends. Let's fix that. So a right Riemann sum. Okay, so before we get into the actual calculation, I just want to give you a sketch, and again, I'm just going to sketch this freehand of this particular function. Like if I ask you to sketch the sine function, and I'll just sketch one period. You might remember your sine function looks like that. And it has constant amplitude of 1, and it oscillates with a period of 2 pi and so forth. And so this would just be your basic sine of x. If I ask you to sketch the x squared, it's your basic parabola, right? Kind of like that. But what happens when you compose them? And remember, this is not a product. As far as the operations here, you're doing two operations. First, you'd square your x value, and then you take the sine of that value that you've gotten after squaring. So here is a sketch of this function, just so you have an idea. And I'll only sketch it over the interval 0 to 5. Now, 0 to 5, so remember what we had said, that the sine of x, the basic sine of x function has a period of 2 pi. Well, when you square that x first, it now goes, you're looking from like 0 to 25. So if you square an x value in this interval, you're going to get numbers that range from 0 to 25. So you'd expect to see more than one kind of period or one interval of oscillation, if you will, when we sketch it. And that's what you'll see. But it also, it looks a little bit different. It's not quite as simple as the sine of x function. So it still starts out at 0, and then it kind of goes up. It looks like a parabola, and then it still hits that peak of 1, and then it goes down and up, and then they start to get like squished together like this, and then up again, and then one more peak, and then it hits 5. It's kind of below the x-axis there. So let me sketch that. So this is the graph of y equals the sine of x squared. Now, if you're trying to replicate this on your graphing utility, it is very important that you use radians, right? So the assumption here is that x is in radians. And we've seen this many times as we do calculus, that calculus that involves trigonometric functions requires your domain variable, your x variable, to be in radians, right? So what is the area that we're trying to approximate here, right? So this is 0, this is 5. Well, it would be all of this. You know, it's everything. It would be all of these that are above, right, between the curve and the x-axis, but then also the ones below. So like all of these, right? And if you kind of think about it, right? Remember what the Riemann sum does. Let me, so basically here is our formula for our basic Riemann sum. K goes from 1 to n, f of x bar k times delta x. And it's this sum where we're taking the function values and we're multiplying them by the delta right now. So I'm not going to try to draw rectangles on this. It's just going to make it a big mess. But if you think about it, some of these function values are positive. So the ones that are above the x-axis would correspond to positive values. And the ones that are below the x-axis would be negative. So it's like some of the terms in our sum would be positive and some would be negative. And when you add them all together, you're going to get actually not just, we need to add something else to this. It's not just an area where like everything is positive. We would actually be computing the approximate net area. So like if you add all these, like the 4 peaks here at the top are going to contribute positive values. The 4 peaks or valleys, if you will, at the bottom here will contribute negative values. So how are they all going to cancel out? Well, it's like, you gain, you lose, and then you have a net at the end, right? So when your function starts to get a little bit more complicated, where part of the region is above the horizontal axis and part of the region is below, we have to change our mindset and think of it more as a net area. But the beauty of this formula is it doesn't change the process, right? So let's see what the process is for this specific example. Okay, so again, remember the interval here is from 0 to 5. You can see it on my sketch. So I will do the interval 0 and 5, and then the next thing you want to do is to compute the delta. So like we know we're using 3 subintervals, so our delta x in this case is the larger x minus the smaller x divided by however many subintervals we're told to use. So in this case we get a delta of 5/3, right, which is possible. So what I'm going to do is just mark off the subintervals now as essentially multiples of 5/3, right? So first you'd go from 0 to 5/3. That will be the first subinterval. And then if I add another 5/3, so make it 10/3, right? And that would give me the second interval. And you can check if you take 10/3. In fact, we can do it on this side. If we do 10/3 and then add 5/3, we will get 15/3, which is 5. So then that will take us to our this endpoint, our b value, right? Okay, so we have our interval, and our method now is to use the right endpoint. So this is my x bar 1. This is my x bar 2. And then this is my x bar 3. Right, so these are the 3 values that we will need, right, to help us create these rectangles that will allow us to approximate this net area. Like how does this whole complicated thing boil down to a single number, right? Okay, so let's put it all together. So our area is approximately, and again, let me write it down symbolically. You're going to have f of the first x bar value, or first endpoint here, 5/3. And then we have to multiply it by the delta. So we have to make sure we multiply by 5/3. And then add to that the next function value. So f of 10/3 times the same constant delta of 5/3. And then finally f of, you could just do 5, or if you wanted to write it 15/3, you could. I'll just write it as 5. And then times 5/3. Right. Okay, so now let's actually plug stuff in. And now remember, the function is the sine of x squared. So it's going to be the sine of 5/3 squared, which is 25/9, times 5/3. Now you might say, do I need to continue writing 5/3 all the time? Well, remember, there is an alternative way that you can kind of simplify not only what you write, but also the number of operations you perform. So let's say since the 5/3 is a common factor, what if I simply factor out the 5/3 and like put it outside here, right? And that way, what it allows me to do, I can first, I'll figure out the function values, then I can add them together, and then at the very end I can do one multiplication by 5/3. So then this is the sine of, so 10/3 squared is 109th, and then plus the sine of 5 squared, which is 25, right? So this is where I'm going to have you try this calculation on your own. I'll tell you what the final answer is and remind you that when you evaluate the sine of 25/9, or the sine of 100/9, or the sine of 25, be sure to use radians, right? And when you do that, add those three numbers together and then multiply by 5/3, and you will get this. Again, I will write down all the digits that I have on my computing device. So it's a negative 1.2830713336, and so on. Again, it's another irrational number. And you get this number, you're like, how on earth is my area negative? But this is where you have to remember that it is a net area. So what this negative number is telling me is that there is more area below the horizontal than above, right? So don't be shocked if you somehow get a negative area when you're doing your Riemann approximations. It's entirely possible. Just keep in mind that it represents the net.